Swayam Prabha. Digital India. Educated India.
All right, good morning, good afternoon. Welcome back to a series of lectures on analysis and design of rigid pavements. We have been looking through several lectures in module 4, which has been on the mechanistic empirical analysis and design of rigid pavements. So let me quickly give you a brief overview of what we've done so far in this class, just to jog your memories. So we had 4 modules. Module 1 was an introduction. The most important thing we learned in the introduction is that there are basically 4 types of rigid pavements that we are concerned with, namely jointed plain concrete pavements, JPCP, jointed reinforced concrete pavements, JRCP, continuously reinforced concrete pavements, CRCP, and pre-stressed concrete pavements, PCP. Now, JRCP is used very lightly in the world. It's rarely found anymore. So we are not going to talk about that in this class. PCP is also a very specialized application. It's actually best taken as of now as part of a structural engineering course. So we're not going to discuss too much on that either. This course has largely been devoted to JPCP as well as CRCP, of which JPCP has been the overwhelming majority of what we've discussed, because indeed the most common type of rigid pavement is also JPCP. But as we've seen in the last couple of lectures, we haven't ignored CRCP. Indeed, the analysis of CRCP is very similar to the analysis of JPCP, with some unique eccentricities and some exceptions, which we had talked about in the previous lecture. Now, that was module 1. Module 2 and 3, we covered the analysis of rigid pavements. Now, I reiterate a very important point, namely that design, the modern idea of design, and we'll see a little bit more about that concept today and in the next lecture. The modern concept of design believes that design is an iterative analysis. That is, we have to keep performing an analysis of a rigid pavement several times before we can reach an acceptable design. That's a fairly modern concept, and that's why we actually spent about half this series of lectures actually on the analysis of rigid pavements before we could go into design. So in analysis, module 2 was the so-called classical methods. Now, if you don't recall, classical methods are old methods. That's basically what the term classical would mean. But really what it means is they are closed form solutions. They are under a series of assumptions. Several people who are much smarter than me, very smart people, about 100 years ago onwards, came up with several closed form solutions. Solutions to what? Solutions to the main governing equation of a rigid pavement, that is the Sophie-Germain equation with an additional correction factor added to account for the presence of or the modeling of subgrade as a Winkler foundation. So for that particular equation, under a series of additional assumptions, we saw several closed form solutions, starting with Westergaard solutions, which is about 100 years old as of now. So starting with Westergaard solutions and then moving on to various other solutions that were developed over time. Similarly, we were also introduced to the concept of Freiberg's equations, where the Freiberg model was used to analyze dowels, not one dowel, but actually a series of dowels, and Freiberg gave a method that can be used to design dowels. Interestingly, you may recall, in dowel design, the concrete is what fails. The dowel as such doesn't fail. Steel is extremely strong. So that's not what fails. It's the concrete which actually fails. And that's a fairly interesting concept to go into. Okay. At the end of module 2, we saw that there were several limitations to using these methods. For example, one of the limitations, probably the most serious limitation, was the assumption of a so-called large slab or infinite slab assumption. That is, it was assumed that wherever the load is, so the load could be at the interior, the load could be at an edge, the load could be at a corner of the slab. But wherever the load is, all the other joints, except the joints which are just next to the load, all the other joints were very far away, such that the effect of those joints was not felt at the position of the load. We saw that this is actually a very big assumption and can lead to significant overestimation of stresses and therefore a pretty wrong design in that respect. And similarly, a significant overestimation of deflections also. It is for that reason that over time, particularly starting from the 1990s, the analysis of rigid pavements has moved away from these so-called classical methods and towards the new modern numerical methods, particularly based on the finite element method. So module 3, we had a very brief overview on the finite element method. Now again, it is impossible to cover FEM in just a couple of lectures. I do recommend, particularly for those of you who have a civil engineering background, those who are civil students or mechanical, I do recommend that you take a formal course on the finite element method. You'll find it particularly useful, not just for pavement engineering, but across all areas of civil engineering. But what we saw is in the finite element method, the first thing we do, which is really, if you think about it, it's a very astonishing assumption to even make. So in the analytical methods, we were seeking an accurate solution, as accurate as possible under certain assumptions. In the finite element method, we actually give up on the idea of getting an accurate solution. So the first sacrifice, so to say, that we make in the finite element method is that we assume that our solution is going to have an error in it. Of course, we would like the error to be small, and generally we try to do certain activities, particularly weighted residual methods, etc., to make sure that that error does become small. But nonetheless, unlike analytical methods, we are not aiming for an accurate solution. We are already doing approximations which are going to give us an error, and we just hope the error is small. What classical methods did was they're trying to solve a partial differential equation, the Sophie-Germain equation, which for those of you who've taken a PDE class or even an ODE class for that matter, you would know that's not particularly easy. That's quite difficult. And indeed, that's why most of the solutions were based on very simplifying assumptions, because without those assumptions, it becomes almost impossible to get such solutions. On the other hand, the finite element method is actually based on the idea that our partial differential equation is now going to be decomposed into a series of algebraic equations. And I had shown you then that when I say series of algebraic equations, I don't mean 2 or 3 equations that you might have solved in high school. What I actually mean is thousands, tens of thousands, lakhs, millions of equations. So we have to solve a very large number of equations, linear equations, algebraic equations, but a very large number of equations have to be solved in order to get an approximate solution. We saw that this approach applied for JPCP, so particularly thin plates, and we saw we can use thin plate elements, so-called NCZ elements. We also saw that this can be used for dowels. So we no longer have to use the Freiberg theory, which itself is based on several assumptions, which we had talked about in module 2. So we no longer have to make those simplifying assumptions. We can instead use fairly sophisticated models to model dowel. And I had introduced you to a particular model, which was namely the component dowel bar model, which actually broke the dowel bar into several pieces and looked at different types of behavior. Please go back and review that lecture in case you forgot any aspects of it. So the nice thing with the finite element method is we can then combine different types of physics. So we can model the plate using a plate theory. We can model the dowel using various forms of beam theory, so Euler-Bernoulli beam or Timoshenko beam, etc., making certain simplifying assumptions on the way. That's what we saw in the previous lectures. And all that gets combined in the finite element method into one large system of equations, which we can then solve to get an approximate solution. And we hope that as the number of discrete points or nodes at which we solve the solution increases, the error will vanish to zero. That is, if the number of elements n tends to infinity, it will never be infinity. It's a finite number, hence the term finite element method. But if the number of elements tended to infinity, then the error would tend to zero. That's the basic idea of the finite element method. All right. So with all of that background, we entered module 4. Now in module 4, I was about the mechanistic empirical design of rigid pavements. And as I mentioned a few minutes ago, one of the main ideas of mechanistic empirical design is that our design is an iterative process. We have to keep doing analysis. So what was mechanistic empirical design? In mechanistic empirical design, we are using physics or mechanics, hence the term mechanistic. We are using physics or mechanics to model our JPCP, or CRCP for that matter, and they're both modeled very similar to each other, as we saw in the previous lecture. So what we are doing is we are using plate theory, we are using dowels, we are using all the analysis tools that we learnt in module 2 and module 3. We are using all those analysis tools to model a JPCP, and what we get out of it is a structural response. In linear elastic mechanics, the structural response is basically stress, strain, and displacement. Now, using stresses, strain, and displacement, we saw that we could calculate something called fatigue damage. And there was also something called differential energy, but let's talk about fatigue damage. So we could calculate a mathematical quantity called fatigue damage, which is based on the idea of fatigue. The idea that with every repetition of a load, we are going to get a small amount of damage, and that adds up over time. So we saw that we could just calculate the fatigue damage, and if fatigue damage meets some kind of failure criteria, generally we use Minor's hypothesis. If the fatigue damage meets some sort of failure criteria, then we say that the trial has passed or the trial section has passed. If it fails the criteria, then it has failed. But we saw, so all of that was mechanistic. We saw that generally fatigue damage is just a mathematical concept. It doesn't really mean much in practical life. As pavement engineers, what we are really concerned is with cracking, with faulting, with punch outs. These various measures of distresses is what we're really interested in. And in module 1, the other thing we learned about was actually different type of distresses. So we saw that we were actually interested in measuring distresses. We don't really care per se what the fatigue damage at the end of 30 or 40 years is. That it doesn't mean much in practical terms. What we do care very much about is what is the amount of cracking we would expect at the end of 30 years or 40 years? What is the amount of punch outs in case of CRCP that we would expect in 40 or 50 years, etc. So that's where the empirical part of mechanistic empirical design comes. We generate a series of empirical functions called transfer functions, which are going to convert fatigue damage or differential energy, depending on what you're calculating. They're going to calculate fatigue damage, which again is a mechanistic response. It's going to be converted to a distress. And this empirical function called transfer functions, they are based on data collected from in-service pavements. They could also be collected from, let's say, large test sections, but vast majority of the data tends to be from in-service pavements. Finally, in the last couple of lectures, we've been looking at one implementation of the mechanistic empirical design philosophy. So I emphasize ME philosophy is a design philosophy. The one thing which we've looked at, which is the AASHTO MEPDG, the Mechanistic Empirical Pavement Design Guide, that is a particular implementation, probably I would say the most sophisticated implementation in the world of mechanistic empirical principles for rigid pavement design. Now, in that, we saw that there were many steps, and we saw finally we first saw how stresses are calculated, mainly for JPCP, but more or less the same thing is used for CRCP as well. We saw how stresses are calculated, we saw how climate is considered, how traffic is considered, and then we saw what the different types of transfer functions were. In the previous 2 lectures, we actually finally separated JPCP and CRCP. We saw that while the analysis of JPCP and CRCP are fairly similar in the sense that the same sort of models, they were neural networks, the same sort of models were being used to calculate fatigue damage, the distresses were different, and therefore on the empirical side, there was a fair amount of difference. There were a couple of other differences also in terms of slab size, which was between the cracks in CRCP, etc. I won't repeat all that, you can go back to that slide. Now, one of the things which I have not been talking about, I've kind of been hinting at it in several lectures, but I've not said it and I've not put it in concrete terms. One of the things I've been talking about is reliability. So I've been showing you figures where I keep telling you that there's some amount of design reliability that has to be added. I showed you the flowcharts from the NCHRP 147A, which is the original documentation for the MEPDG. I showed you flowcharts from there where they kept saying that you have to also provide some user-defined reliability. And I told you in the last 2 lectures to just pause on reliability for a minute, and I will come back and talk about it. So after that very long introduction, today's lecture is actually going to fill in that gap which I left. Lecture 32 today is actually going to be on reliability analysis. So in today's lecture, I'm going to tell you what is the mathematical concept behind reliability. What is reliability? What does it mean for something to be reliable? And in the opposite question, what does it mean for something to be unreliable or for something to fail? And then once you understand the mathematical concept behind reliability, I'll then show you how the pavement ME or the AASHTO MEPDG, how that incorporates reliability. We will look at both JPCP and CRCP. I can tell you straight away initially, the reliability is included empirically. So we, as of yet, do not have a good way to incorporate reliability mechanistically. So we choose to do it empirically instead. And that's the current approach. Okay, so just to kind of jog your interest in this, let me ask some discussion questions. So suppose we have 2 different pavements, right? Let's say they are very, very similar pavements. Let's say they are very close to each other. They more or less get the same amount of traffic. Because they're close to each other, they get basically the same amount of climate. Let's say they're basically the same in their design, so almost the same type of soil, exactly the same type of pavement structure, etc. They're almost, on paper at least, they look perfectly identical to each other in all respects. In that case, let me ask you, do you expect that both those pavements, let's say they're JPCP, do you expect both those JPCP sections to have the same amount of cracking, exactly the same amount of cracking at the end of their service life? For example, if pavement 1 has, let's say, 25% cracking. Now, Just to recall, what does 25% cracking mean? It means that if you take a survey over a long distance, that distance should be several kilometers. If you take a survey over a long distance, you'll find that out of every 100 pavements, or let's say out of every 4 slabs, 1 slab is cracked, 25%. So that's what it means to be 25% cracking. So let's say pavement 1 had 25% cracking. Do you expect that if you did this exercise and you went out, would you also get exactly the same number, 25% cracking in pavement 2? And again, pavement 1 and pavement 2 are almost, on paper at least, they're basically identical to each other. Do you expect that to happen? Let's look at 2 different aspects of the question. Do you expect that to happen in mechanistic empirical design? Namely, if I asked you to design, so if I gave you the pavement and I told you that everything is the same, climate is the same, traffic conditions are the same, soil conditions are the same, etc. If you do the mechanistic empirical design, as we've discussed in the previous lectures, would you get the same expected percentage cracking at the end of the service life? The answer is a resounding yes. Everything we've done so far is what we call a deterministic process. Let me write it down. Deterministic. This is a deterministic process. A deterministic process is a process where we know the exact answer every time. So for a fixed set of inputs, we will always get the same output. So let's back up a little bit and ask, why do we say that the ME design, to the extent that we've learned it so far, why do I say that ME design is deterministic? Well, consider what all the inputs were. There was traffic, there was soil, there was pavement structure, so thickness, etc. There was climate. All of these are the same. Now, these go into calculating stress. If you have the same climate, which means you have the same delta T. The delta T incorporates the temperature gradient, the non-linearity, the moisture, the built-in curling, etc. So all that is in there. So if you have the same delta T, if you have the same axial load spectrum, if you have same layers, same material properties, you're going to get the same stress every time, right? It's just going into a calculation. The calculation is just going to give out an answer. There's no variability in that answer. And therefore, from that answer, then when you calculate the result, when you put into a transfer function, the transfer function also has no uncertainty in it. It takes an input, it gives you an output. Every time the input is the same, it gives you exactly the same output. And so, at least at the level of mechanistic empirical design, up to the point that we've learnt it, we will basically always get the same answer if our input conditions are exactly the same. But let's ask in real life. In real life, if we actually had 2 pavements which at least on paper look exactly the same, design is the same, input is the same, everything looks the same if you just look at the DPR or basically what the construction report was. If you look at all of that, then you would expect, yes, I should be getting, the design says I should be getting the same amount of cracking. Therefore, you would think you would get the same amount of cracking, but in real life, you actually will not. So if you actually do this, you try to see, and this has been done in the past, if you take 2 very similar pavements and then try to do a design out of them, you try to go out in the field and see how they actually perform. So you're not doing a design, you're actually checking performance of an existing pavement. You will see that even if the pavements are almost identical to each other, you can get a fair amount of deviation in the final distresses, for example, cracking or faulting, etc. So mathematically, the mechanistic empirical design, as we've learned so far, is a deterministic process. It's always giving us the same answer for the same set of inputs. In reality, however, it doesn't happen. Identical pavements or nearly identical pavements can result in very different amount of distresses at the end of their service life. Why is that the case? Why do we see this? So observationally, I'm telling you, this is what we would observe, and you're welcome to try this on your own also, and you'll see this is also what you observe. So why is this the case? There can be several reasons. For example, you can have some random localized weather episodes. So a very good example of this, which I'm sure all of you recognized, is when it rains, some part of the city, for example, in the monsoon or pre-monsoon showers more usually, it might rain in some parts of the city. So the newspaper or the news will tell you it's raining in XYZ city. But then you might be sitting in the city and saying, hello, it's not raining here. It's cloudy or it's even sunny over here. I'm not getting any rain, but the news is telling me it's raining. Because weather conditions can vary dramatically even locally. So even within the same city, you can have some places where it's raining, some places where it's not. Some places where it's very cloudy, some places where it's bright and sunny. So you can have very random localized weather episodes which can be difficult to capture in our input models, because at the end of the day, for the pavements in a particular area, As far as design is concerned, we assume they are undergoing the same type of climate. That is, we use generally the same climate information for a given location. We don't go down and do for every little locality a separate climate analysis. So, due to random localized weather episodes, we can have some variability in the results. These random localized episodes will not be captured in the design. Secondly, there could be some variation in pavement materials and structures. Recall that we learned when we talked about back in module 1, we had a very brief discussion on characterization of concrete for the purpose of rigid pavements. And then I had introduced you this term, which I've kept coming back to, which is FCK, which is the characteristic compressive strength. And if you recall the characteristic compressive strength, this was basically the 95th percentile strength. So basically, if we take a number of specimens and we test them, and we take the 95th percentile strength of those of the results, then that basically is what FCK is. So what this should implicitly tell you is, if for the very same mix design, if I cast a number of cubes or cylinders and I test them for the compressive strength, I will not get the same answer for all of them. This is what we would call material variability. So one level of material variability, it can happen because the microstructure of the concrete can vary from place to place. Somewhere you have a little more aggregate, somewhere a little less aggregate. In some places, the water happened to be well distributed. In some cases, the water was not very well distributed. These kind of things happen in construction. Indeed, even in the lab, these kind of things happen. So you can have some amount of variation, and generally will have some amount of variation in pavement materials as well as structures. What do we mean by structures? So generally, so far what we've been doing, we've been talking about thickness of the layers as one single value. So example, I could say that I'm providing a 400 mm, let's say GSB, granular subbase. That's what you would put in your design. Now, if you go out in the field and let's say the contractor has laid 10 kilometers of pavement, do you think you will get exactly 400 mm GSB across all those 10 kilometers? The answer is no. Some amount of variability will happen. After all, it's heavy construction equipment. Somewhere it might be applying a little more settlement, somewhere there might be a little less. Some aggregates might be just randomly a little bit bigger here, a little bit smaller there, etc. So you will never actually get 400 mm, and indeed if you look at how specifications are made for construction, they always say 400 plus or minus some range. It could be say a 5 to 10% tolerance or something. So there will generally be some amount of tolerance. So you will never get exactly the same pavement structure throughout the entire length. There's going to be some variations. Now this is despite the design saying what the pavement structure is. So keep that in mind. Just because the design said something, don't assume that's what you're getting in the field also. And then you can have variations in loading. After all, although we said that the inputs are the same or the loading are the same, you can have minor variations in loading. One day there was a cricket match and one of the roads was closer to the stadium than the other. More people, just for a couple of hours, more people decided to go on that road. Overall, that's barely going to make any difference to 30 years worth of traffic. But because there is still some amount of slight difference which came because of that, because of which the final distresses which are developed will also be different. So what we see are, these are sort of practical issues which come up. So far we've been talking about all our design inputs in a very idealized or idealistic way, that these are the exact inputs, this is what we're going to do, and now we calculate the final design. But what we see is actually all our inputs essentially have a fair amount of uncertainty in them. Some more, some less. So for example, weather can actually be very uncertain. It's actually quite difficult to predict the weather 30, 40 years into the future. And as we know, climate is changing, so we really have very little understanding of this process as of this point. And pavement materials and structures, it's very difficult to predict how these are changing on the field because it really varies by individual construction case, in the contractor, the type of contract, how it's being executed, lot of sources of variability. And similarly in loading, it's just impossible to say what the road is going to be used for in the future with a great deal of certainty. There's going to be a fair amount of uncertainty all this. So that's what we find is that the development of distresses in pavements in real life is inherently a probabilistic process. That is, even if we have the same inputs or we think we have generally the same inputs, the outputs, that is the distresses, they are not going to be exactly the same. There will be some amount of variation just purely because of these random things which we just talked about in the previous slide. Thus, almost none of the inputs that we use in design are deterministic. I should add, the way we've done design so far, all the inputs are deterministic. We've only asked for one value of say of compressive strength or flexural strength. We've asked for only one value of thickness, one axle load spectrum. So far, we've never seen any uncertainty in these values also. But if in real life, if we know that these inputs have a probabilistic nature, that is, you don't get an exact value, you get a probability, you get it within some range. And we know that the distresses in real life are also probabilistic in nature, that even if you know all the inputs within a certain range, even the outputs then are still going to have some variability within a certain range. So if in real life our pavement performance is probabilistic, then really our pavement design must also reflect this probabilistic nature. That so far we've been doing deterministic design, that clearly is not correct for the way we are doing design. We should be taking into account that pavement performance is probabilistic into our designs. So as a reminder, this is a figure which I've shown you many times. This is the general process of how we do a mechanistic empirical design. This actually applies for both flexible and rigid pavements. Of course, I'm speaking specifically for rigid pavements at this point. That is, we take a set of inputs, and again, each of these inputs now has some variability. We do a structural response model out of those inputs. There is no variability in the structural response models. Whatever you give the input, as long as the input is the same, you'll always get the same output. Stress, displacement, strain, etc. You'll always get the same outputs. The pavement distresses, namely the transfer functions, those are also deterministic. So as long as you give it the same stress, you will get out the same amount of fatigue damage, and from fatigue damage, you'll get the same amount of, say, cracking or faulting, etc. What we've seen here is then at this point, after this, so once our transfer function calculates our distress, then we have shown this, and I've never explained it properly. I'll actually explain it today. This reliability term is then added at this point. Just as a note, you will see, if you go back to the mechanistic empirical design guide, that is a couple of lectures we've had on AASHTO pavement ME, the reliability is actually added over here to inputs. I sort of disagree with that, and I'll show you why. Reliability, strictly speaking, should be added over here. So it's at this point where reliability becomes an input. Reliability is not an input at the first stage. Anyway, I'll explain that in a couple of minutes. So reliability is added to the output of the transfer function. From there, we get some sort of pavement performance under some amount of reliability. And by the way, I haven't explained what reliability is yet. I'm going to get to it. But from reliability, you can understand that some amount of probability is being considered when we talk about reliability. So then again, we compare it to a pavement failure criteria. If it passes, good, that's a final design. If it doesn't pass, then you go back and update it, etc. By the way, even updating this is not a very straightforward process. In next lecture, actually, we'll see how to properly update these trial structures. There's quite a lot of science behind it. But for now, leave that aside. But reliability is where, so it comes in at the end of this process when we have calculated our distresses with the transfer function. At that point, we have to account for the probabilistic nature of the solution, and that comes in through this term reliability. So what is reliability? I'll explain to you what it means in terms of the mechanistic empirical pavement design guide in a couple of minutes. But before that, I just want to talk mathematically. What is reliability? And even before that, let's ask ourselves in colloquial words and simple words, what is reliability? If I tell you that, okay, I've just bought, let's say I bought a car, and the general feeling, and that's what my friends told me, is that the car is very reliable. What does that mean? It means that when I need it, when I need to do something, for example, if I need to drive for a couple of hours, it will be able to do that. That is, for whatever I need the car or whatever I need the item, it's going to give me the desired level of performance. That's basically what we mean by reliable. Desired level of performance every time, sometimes, half the time. That brings us to the question of what is the probability of reliability. That is, what is the probability that whatever item I'm looking at, so whether it's a car or whether it's a road, etc., whatever item I'm looking at, what is the probability that it's going to function as desired? That number is basically what we call reliability. So to give you a formal term, formally, reliability is the probability that a product, system or service will perform its intended function adequately. Now, the intended function is the key word here. It can mean anything. I just gave you the example that the intended function of a car is to let you drive. The intended function of a road, I won't answer that yet. You want to think about it a little bit. What is the intended function of a road? And this goes back to distresses. So we will answer that, but just as a quick tease to you, I'll just let you pause for a minute and think, what is the intended function of a road and how can I relate this definition of reliability? So instead of saying product, system or service, if I had said a JPCP section, then what does that mean? The intended functional, it's meeting the intended function adequately. Okay, keeping that aside, let's go on to our mathematical description. Suppose that the output of a system has a probability of x. That means if we give it an input of x. Now, by the way, x here, I'm just writing it as one variable. It could actually be a series of variables, right? So if I put an x bar down here, it turns it into a vector. So it doesn't have to be x as one scalar value. It could be a vector of inputs also. But just generally, I'm saying if we have a system and that system takes a series of inputs x, and the outputs are defined by the function f of x. And furthermore, we say that the outputs, you don't get one value of the output, you can get a variety of values, and the probability of those outputs are defined by this probability function. Sometimes we call this a probability distribution function, PDF. The probability distribution function is f of x. Now, suppose that if we have a system input x, so capital X, suppose that I want, say, a input of capital X. I want to know at the input of capital X, what is the probability that the system will give me a solution that I intend? In other words, the reliability R of the system is defined as the probability that the output at some input capital X will be less than some value R. That is, f of x less than or equal to capital X is equal to R. Putting this in a much more simplistic term, let's think of that car example again. Let's say that my intended functionality of the car is that it should be able to drive. That when I put put on the keys, when I press the accelerator, the engine should turn on. What is the probability that the engine will turn on? So if my particular case is that the engine should turn on, what is the probability that the engine should turn on? If it could be 5%, that means 5% of the time it will turn on, 95% of the time it won't turn on. Or it could be 50%. Half the time it turns on, half the time it does not. This number, 5%, 50%, 70, 80, whatever the number is. This number is what we call reliability. The probability that the system will perform adequately to whatever extent I want it to perform is called reliability. And mathematically, it is the probability that it is basically the probability that that given an input x, the probability of that input f of x less than or equal to x is called the reliability. Now, mathematically, this can be shown in a little more sophisticated manner. So here I showed you that R, which is the reliability, is the probability that the function f of x, that the output x is less than or equal to some desired output capital X. Mathematically, this can also be written as a cumulative distribution function. So here I said that this function lowercase f of x is called a probability distribution function, PDF. And then the function with the integral of that function from, let's say, minus infinity up to the desired value capital X. That is what we call the cumulative distribution function, or CDF, of that particular value x. And we generally show that with this capital F of capital X. So what we say is the reliability of the function, at a particular value x, capital X, is the value of the the cumulative probability distribution function of that function at that value x. So R is f of capital X, which with our previous definition is f of x less than or equal to x, which is the integral from minus infinity to capital X of f of x dx. This x here is a dummy variable. Thus, what we can find is if somehow we know the underlying probability distribution of the system. So if somehow I could say I know what is the probability distribution that the car is going to turn on or the car is going to turn off. If somehow I knew that, then I can evaluate the reliability of the output at some input x. So really, if I'm interested, let's get back to a concrete example. If I'm interested in a JPCP section and I want to know what is the reliability. In other words, if I'm predicting that I'm going to get 20% cracking at the end of 30 years, what is the reliability of that? How do I know what is the probability of getting that 20% cracking? For that, we have to know what is the underlying distribution, what is the underlying probability distribution of cracking to occur, that is f of x. How do we get that distribution? How do we know what is the probability of our pavement cracking? There are basically, for rigid pavements, there are two ways that we can do this. So again, our system, the rigid pavement system, we have a series of inputs. This is what I had in the slide over here. We have a series of inputs: materials, climate, traffic variability, etc. We have these series of inputs. Now, here an important term I had: variability, and I haven't talked about that. So let me talk a little more about it. So we know that each of our inputs has some variability. Each of our inputs has a probability distribution function. We could try to generate the probability distribution function for each and every input, and then we can try a variety of different combinations. For example, if we know that strength and thickness have a probability distribution function, we can try within that distribution function, we can try taking a value of strength, we can try taking a value of thickness, we can predict the performance. We can take another combination and predict the performance. We keep doing this multiple times in what is called a Monte Carlo simulation. We do this multiple times, and then we might get a probability distribution of the output. That's one way to do it. The other way is, let's not consider the probability distribution of the inputs. Let's assume the inputs we are taking some design values, but they are deterministic values. Let's say the inputs we are taking deterministic values, and we are going to account for the probability distribution of only the output. So option 1, we are taking for every input, and there are a very large number of inputs in mechanistic empirical design. Option 1, we are taking every input, we are considering the probability distribution function of every input, doing a large number of simulations, and then trying to get a probability distribution of the output. And option 2 is, let's directly consider the probability distribution of the output and consider the inputs to all be deterministic. Now, I think I've been hinting at it, but I hope many of you understood. Option 1 is not that easy. It's actually quite a challenging option to do. Why? Well, first of all, we have a lot of inputs, right? So just in mechanistic empirical design, and we'll actually see this in the next lecture also. In mechanistic empirical design, we are easily dealing with 10, 20, even 50 inputs. So each input variable would have its own probability distribution. So climate has its own probability distribution. So air temperature, for example, has its own probability distribution. Traffic has its own probability distribution, etc. The strength of the materials, the thickness of the layers, all of them have their own probability distributions. It is difficult, first of all, to generate these probability distributions, and generally there is no guarantee that all these distributions are going to be normal. So what is a normal distribution? I hope some of you have taken a probability distribution class, but if not, I'll just give you a very general idea. A normal distribution is basically this bell-shaped distribution, that we say that around some value, which you generally call the mean, nu, around some value which is the mean, our value can vary. So the x-axis here is this x. So the value of x varies around a mean, and the amount of variation we get is defined by the variance, which is sigma square, or the standard deviation, which is sigma. The good thing about a normal distribution is we can do a lot with the normal distribution. If we say that the underlying probability distribution is a normal distribution, we have a lot of mathematical tools at hand in order to analyze it. And generally in engineering, we like normal distributions. We're very comfortable with them. A lot of our tools make it very easy for us to analyze normal distributions. The problem is, with option 1, we have so many variables, and each of the variables has its own probability distribution, that each of the properties has its own probability distribution, and there is no guarantee that all of them are going to be normal. There can be other types. What are other types? There are plenty of other types. The uniform distribution, there's a gamma distribution, there's a beta distribution. If you just open a textbook of probability and statistics, you will easily see at least a dozen or 2 dozen different types of distributions. So there is no guarantee that all our distributions are normal distributions. Indeed, some could be one type of distribution, some could be another type of distribution. Very quickly, the mathematics starts getting very challenging. If we have to consider so many different probability distributions, first of all, to even construct the probability distribution, which means, do you know what is the value of nu for the variable that you're accounting for? Do you know what is the value of sigma for the variable that you're accounting for? In order to just figure this out and calculate it for every project itself is very difficult. And then to have to take into account every possible probability distribution of them, mathematically it's very challenging. And that's why option 1, although it seems straightforward, it seems like what should be done, is actually not done in practice. Option 2 is done in practice because, and there is one very strong reason, I explained what is the downsides of option 1, but actually option 2 is used not because of the downsides of option 1, but because of one very important advantage that option 2 provides. Remember, in option 2 is again where we do not account for the probability distribution of the input values or the input variables. We account for the probability distribution of the output, and the output in this case is the distresses. So we don't take into account the probability distribution of the thickness, materials, climate, etc. Instead, we only take into account a probability distribution of cracking, of faulting, of punch outs, etc. The advantage of this is as follows. The output, cracking, faulting, etc., the output is basically going to have a combined effect of so the uncertainty in the output is going to have a combined effect of the uncertainties contained in the inputs. So the inputs have all types of uncertainties. You can have a normal distribution, log normal distribution, uniform distribution, etc. You have a variety of different distributions in the inputs. And there is a particular theory in mathematics called the central limit theorem. The central limit theorem says that as the probability, well, this is not exactly the definition of the central limit theorem, but it's as applied to our problem. As the probability distribution of the distresses, which is the output, is a result of the joint probability distribution of individual inputs. So I should put here joint. It's a result of the joint probability distribution of the individual inputs. The central limit theorem says that this joint probability distribution, so when the output is a probability distribution which is depending on the probability distribution of the individual inputs, whatever those probability distributions are. The central limit theorem in mathematics says when you take the joint probability distribution of a large number of distributions, which can be from any underlying distribution, then that joint probability distribution will tend towards a normal distribution. In other words, let's say I have 50 inputs, thickness, climate, etc. Each of them has its own probability distribution, but all of them are going to contribute to the uncertainty or the probability distribution of the output. Then the central limit theorem says the probability distribution of the output will be a normal distribution. That's a very powerful statement. I just said previously, if we have to account for every distribution, it's quite difficult mathematically. And as engineers, we prefer to work with normal distributions. We have a lot of understanding on how to deal with them. And so the central limit theorem says that if you don't account for the inputs, the output, that is, the inputs are going to be of a variety of distributions. The output will always tend towards a normal distribution. And indeed, in practice, that's also what we see, that the output cracking, faulting, etc., they tend to follow a normal distribution. This is why option 2 is almost always used. We still have to collect a lot of data for option 2. I'll talk about how we can take this, how we can actually construct option 2 and how we can implement it into practice. But the advantage that option 2 gives us is that the uncertainty in the distresses is basically almost always going to be a normal distribution. And we are very good at dealing with normal distributions. So what's a normal distribution? I gave you a schematic of it, that basically we have a mean, and around the mean, we'll have a symmetric bell curve shape. And that's how far away these goes. It's basically going to go from minus infinity to infinity. But whether it's very thin or whether it's very thick, etc., in the middle, what is that particular distribution? That depends on the variance or the standard deviation sigma. So generally, we define the normal distribution like this. We say it's f of x. So this notation might be a little new to you. It's not particularly important, but I just want to show it formally. So f of x is the probability distribution of x, which is going to be a normal distribution. Nu and sigma, after writing in this semicolon, nu and sigma there basically mean those are the parameters of the distribution. So x is this unknown value, the x-axis, which is so x is basically going from minus infinity to infinity. And nu and sigma are parameters that have to be provided for the distribution. So this is what the normal distribution looks like. It's fairly sophisticated, right? So you've got one important thing, you've got an x minus nu over sigma, and that's into some sort of exponential function. So it's definitely some exponential function. Actually, it's an exponent of a square term, so even more interesting. But what I just want to remember is it does contain this x minus nu over sigma. So whatever is x, the mean gets subtracted from it, and then it gets divided by the standard deviation. We'll get back to this in very soon. The cumulative distribution function, this can basically come from integral of minus infinity to x, let's say f of y dy. This is the cumulative distribution function. This will actually work out to this. This ERF is what we call the error function. You may or may not have seen it in the past. It's not important. The only thing to know, computers are very good at calculating the error function. So you just understand that the error function is something that we have full knowledge of. It's not a problem to deal with it mathematically. So this is what the cumulative distribution function of a normal distribution looks like. So the question is, what is the reliability? If we are talking about if the reliability of system is R, then what we really want to know, if we want the system to have a reliability of R, then we would like to know what is the value of XR such that f of XR is equal to R, here capital F. So this is the cumulative distribution function. So really, the problem which we face in engineering is, if we want our system to have a certain amount of reliability, we would like to know what is this value? What is this value of, let's say, cracking or distress, which will give us that amount of reliability. So actually we're trying to solve the inverse problem. Now, one note, we generally don't deal with XR directly. So X here could be cracking, it could be faulting, etc. We would generally prefer to normalize this to be a simple value, and that value is typically shown in a variable Z. So generally we rewrite X as follows. We change the variable. Instead of doing f of X, we actually prefer to do f of Z, and where Z is defined as X minus nu over sigma. In which case, note here, the parameters are nu and sigma. If I define Z as X minus nu over sigma, then I'm going to get the mu of Z, that is the mean of Z is going to be 1, and its standard deviation or variance actually is going to be 0. So this type of a function where I have normalized the normal distribution. So instead of the normal distribution being with respect to nu over sigma, I've changed the variable X so that the mean is 1 and the standard deviation or variance is 0. And that is what I call a standard normal distribution. Why do we want to do this in practice? Because we know a lot about the standard normal deviation. They are good formulas, there are published tables that will basically tell you, if I give you this, if I ask you what is the value at, well, if I ask you what is R, what value of Z corresponds to some desired value of R, I can answer this very, very accurately. There are very good mathematical tools to do this. So that's generally why we want something like this. Now, so then the problem changes slightly, that instead of using this normal distribution, we now normalize everything to the mean and the standard deviation, and we use a standard normal distribution. So the question changes a little bit slightly. Given that we want some reliability in R, we want to know what is ZR that corresponds to that reliability. And that ZR is sometimes just called the Z score or Z score, depending which country you're in. So that's sometimes called the Z score. So the problem of reliability comes down to, if you want your system, the output of the system to have a certain amount of reliability, then this is the value which gives you that reliability. That's the Z score which gives you that reliability. And again, the reason we do it on the standard normal distribution is because we have very good mathematical tools that can give it to us very easily. Now, in mechanistic, so that's all about reliability, right? That's the mathematical concept of reliability. Let's start going back into mechanistic empirical design. So again, in ME design, as of now, what we've done is we ignore the variability in the inputs. Whatever the inputs are, we take whatever values we have and we calculate the distresses using the transfer functions. That's the point that we're at. Now, in mechanistic empirical design, we make an assumption that the output of this transfer function is a 50% reliability. And you may want to note that Z of 0.5, that is when the reliability is 0.5, then the corresponding Z value is 0. So that's something it's an interesting thing to just note, that the 50% reliability occurs when the Z score is 0. By the way, I think I made a mistake here. Yeah, it should be 0, 1. So the mean is 0 and the standard deviation is 1, or the variance is 1. So what this says is, so we make an assumption in ME design that whatever output we are getting from our transfer function, that has a 50% reliability. What does that mean in practice? What we are basically saying is the real distress. So we have calculated some distresses in our design. What we are saying, half the time the actual distresses in the field will be more than that value, and half the time the actual distresses will be less than that value. So the real distresses could be less than or greater than the value evaluated using the transfer function with equal probability. You will agree with me that's not particularly useful for design. It seems quite useless. We have calculated a value, half the time we are going to be greater than that value, half the time we are going to be less than that value. That's not particularly useful. Indeed, we would rather have a system which has a higher reliability. So 50% reliability is a starting point. We are generally not very happy with 50% reliability except for very small payments, and we'll see a little bit about that towards the end of the lecture. Another way to interpret reliability, and this I find many students are more comfortable interpreting in this way, that's why I'm just mentioning it to you. Another way to interpret reliability, so reliability we had previously said is basically f of x less than or equal to capital X. This is reliability. We could also define something called failure. Failure is basically 1 minus of this, which we sometimes write as f of x is greater than or equal to x. So if reliability is, what is the probability that the output x, small x, is going to be less than or equal to some threshold or some value, capital X. This part is called reliability. 1 minus reliability is probability of failure, which is what is the probability that my output is going to be greater than some threshold. So this is therefore called the probability of failure. So one way to interpret this, so the assumption that whatever we get from a transfer function is 50% reliability, I can take 1 minus of that, or 100 minus 50%, it's still 50%. What that is saying is, if I construct my pavement exactly according to the design, so if I use the same value that that was used by the transfer function or by the ME design, 50% of the time my road is going to fail before the expected service life. You will agree with me that is far too high. So half the time I'm going to have premature failure, half the time the road is going to last longer. Half the time premature failure is a completely unacceptable situation, practically speaking. We would like this to be much lower. We do not want the failure to be 50%. So what I have in this graph is I've got time over here. This is what a design would look like. Time, and this could be any distress. In this case, IRI is plotted over here. So this solid line is basically what your mechanistic empirical model is predicting. It's predicting this is how the IRI is going to increase. And as I said, we assume that the prediction we get out of it is considered to be 50%. So what we have here then is, that means 50% of the time my pavement is going to fail. Obviously, we don't want that. So what we would like to do is, we would like to shift this upwards. We would like to somehow increase the IRI, which is to say that the amount of time our pavement will fail, failure rate is basically over here. The percentage that the pavement will fail starts decreasing, or in other words, the reliability of the value starts increasing. That's what's shown in this orange over here. So what we see here, if this is the value at R is equal to 50% reliability, and this dotted line is at any other R is greater than 50. At R is greater than 50, what we're seeing is this orange area. So if you consider the orange area as the value after the mean value, so it's from the mean to infinity, and the rest of it is minus infinity to the mean. This orange value, as you see, as we increase the reliability, what we basically want is for this orange area to shrink, which effectively means we are increasing the predicted IRI. That's basically how reliability works. If our design tells us that we are going to have a certain amount of IRI at the end, we would like to increase it by some amount, such that that increase is going to make our result more reliable. Therefore, if we know some value of Z at a particular value of R, if we know the value of Z, we can recalculate XR accordingly. So remember, we have defined Z is equal to X minus mu over sigma. So now if we can calculate ZR, we can calculate XR, which is what we care about. We can calculate it using this formula. This is pretty straightforward. The mean value, this nu, this is the 50% reliability. This is what our transfer function is evaluating. That means this is what we are going to get out of our mechanistic empirical design process if we don't consider reliability. If we consider reliability, we have to get this additional term ZR into sigma. I already said ZR we can get assuming it's a normal distribution, which is a good assumption for the distresses. Assuming it's a normal distribution, we can very easily calculate ZR using tables or any spreadsheet program. It's quite easy. What we need to know is sigma. So if we know nu is what we're going to get out of our design. ZR is something we can calculate depending on what reliability you want. Sigma is what is left. So to evaluate XR, we need to know something about the standard deviation of the output sigma. How do we know that? There are many ways to know it. I'll tell you how pavement ME does it. In pavement ME, the standard deviation is actually determined as a function of the predicted distress based on some empirical data. In other words, we say this sigma is some sigma of nu. That is based on whatever the predicted value or the mean value is, the standard deviation varies accordingly. So here is an example. This is actually how the data came out. So what they had is, they had some predicted cracking. So using the mechanistic empirical design, they got some predicted cracking. This is percent. This is at a reliability of 50%. So this is the predicted value at a reliability of 50%. Then what they saw is, they actually compared it to the standard deviation of various sections that they had gone out and measured. So they had gone out and measured various sections. What they found was, when the mechanistic model is predicting, say, 10% cracking, then they went and then saw, okay, what are the sections where 10% cracking is predicted? Obviously, for those sections, they didn't find 10% cracking. They found 9, 8, 10, 11, 12. There's some amount of a distribution over there. They calculated what is the standard deviation of that distribution. So to put it in a different way, whatever sections were supposed to be very similar to the design, they calculated whatever is the distress from the design. Whatever sections were supposed to behave very closely to the design, they went and measured the actual distress They got the mean, of course, but then they also got the standard deviation. So you can construct a plot like this where you have the predicted cracking, let's say x, and then you have the standard deviation of x put over here, and you can fit it to a curve. This is basically what we have over here. So this predicted value x, this is the mean value. This is that 50% reliability value. We now have a function of standard deviation as a function of the mean predicted value. This is what we want. So the way it works is to show these exact, and these equations I'm all getting from the mechanistic empirical design guide. So here, for example, for cracking, we can write cracking at any predicted reliability level P, that's under this crack P, is equal to the mean cracking. The mean cracking is what we get from the transfer functions. Please go back 2 lectures ago, I showed you the transfer function for this, so I won't repeat it, plus some ZP, this is the Z score corresponding to that reliability R or P, that we can calculate, into the standard deviation of cracking. And what is the standard deviation of cracking? In MEPDG, they give us this formula. It is again a function of cracking. This is the cracking at 50% reliability. So we calculate the crack. This is, by the way, the same thing as this crack mean. So this crack over here is equal to this crack mean over here. So we calculate the mean, and using the mean value, we also calculate the standard deviation using this empirical function which has been obtained through field data. So this is how we basically use this function through field data and create a function for the standard deviation. And from that, we can then, once we have the standard deviation, we can calculate the cracking at any desired reliability level. What is the desired reliability level? What should we be designing for? What reliability is considered adequate? This is actually a policy decision. There's no engineering answer. This is a policy decision. For example, on low volume roads on local streets, maybe those are not very important roads. You don't need it to be very reliable. It may be okay if they actually fail maybe 50% or 30% of the time. Whereas for major roads, expressways or highways, that is not acceptable at all. We may want the reliability to be 90-95%, that we will basically not tolerate a large amount of distresses developing on the road. So what NCHRP 137A, again, there's no Indian equivalent to this per se. We'll talk about the Indian practice a couple of lectures from now, but what NCHRP 137A or the MEPDG recommends is for interstate or freeways, these are basically those expressways, or for highways, which you can call principal arterials, they recommend about 80 to 97 or 75 to 97% reliability. It varies a little bit between urban and rural. That's because of the nature of traffic. Whereas if you get down to local streets and urban streets, they actually recommend 50 to 75%, which means it can fail 50% of the time, 25% of the time. It's okay for particular local roads. So the choice of reliability R is really a policy decision, and every country, every agency is going to have its own idea for how reliable their design needs to be. Why is it important to fix the reliability? Well, what I have over here on this graph is, on the x-axis is the age in months, the y-axis is the predicted JPCP cracking. This is the 50% reliability line down here. If we see, as we increase the desired reliability, the amount of JPCP cracking is increasing. So for example, let's say that I have a section, and as a policy, I'm willing to tolerate at the end of the end of the design life, I'm willing to tolerate 20% cracking, right? If I did my reliability analysis at 50%, maybe it's a local road, my analysis would tell me at the end of my design period, I have 10% cracking. Well, 10 is less than 20, so this is okay. However, if I decided, if it was a very important road and let's say I needed to have 95% reliability, then what I get is at a 95% reliability level, I actually end up with maybe 27% cracking, which is above 20, which means this is an unacceptable design. This is a failed design, and now I have to go back and change the design. So the level of reliability actually ends up determining what your design is very strongly. Whether your design passed or failed is very closely related to reliability. As you shall see in the next lecture, this reliability eventually, in the way it's done today, what the practice is, basically what this says is that if you increase your reliability, you're going to end up increasing the thickness of the JPCP. That's basically how the whole design is done as of today. So why this is important? Let's say that we had a thickness of 300 mm. At 50% reliability, we got 10% cracking. That was fine. My threshold is 20. But at 95% reliability, I've exceeded my threshold. So now from 300 mm, maybe I need 325, maybe I need 350. Cost is going up. So as I increase my reliability, I'm going to have to spend more. I'm going to have to make a thicker section. That's why you have to be careful what reliability you use. All roads we cannot have with the same level of reliability. It's going to increase our cost. It becomes uneconomical. Okay. For faulting, I'll just quickly go through the other ones. So for faulting, again, the faulting at a reliability R is the mean faulting, mean as in 50%. So is the faulting at 50% reliability plus the Z score, which we can get for the reliability value, into the standard deviation of faulting, which is this particular function. It happens to be a square root. So it's an empirical function. It can take any weird form. You can say a large number of zeros over here, whatever the function says. So it is this particular function. And similarly for IRI, they provide this particular function. You see the C1, C2, C3, these are some constants, and this SE, some constants. And then for punch outs, SP, which is the standard deviation for punch outs, this happens to be a power law. So as you see, these are empirical functions. Sometimes it's a power law, sometimes it's an algebraic equation. It's whatever fit best for that particular case. Okay, so in today's lecture, we talked about reliability. As I hinted very slightly in today's lecture, eventually the effect of reliability, increasing the desired reliability, is to increase the thickness of our pavement. Why is that the case? Why can't increasing reliability be compensated from somewhere else? That actually brings us to a question of how we are doing this design optimization. And that's going to be the subject of the next lecture. So I will see you then. Thank you.